unsigned binary multiplication is not work if both the multiplicand and multiplier are negative. The reason is that the bit of the multiplier no longer corresponds to the shift or multiplication that might take place. There are a number of ways out of this dilemma. One of the most common of these is both algorithms. Both algorithms have the benefit of speeding up the multiplication process relative to a more straightforward approach. Now, what is both algorithms? Firstly, multiplier and multiplicand are played in the Q and M register repeatedly. This is also a 1-bit register played logically to the right of the least significant bit Q0 of the Q register and designated Q-1. The result of the multiplication will appear in the A and Q register. A and Q-1 are initialized to 0. Control logic scan the bit of the multiplier one at a time. Now, as each bit is exempt, the bit to its right is also exempt. If the two bits are sent 1, 1 or 0, 0, then all of the bits of the A, Q and Q-1 register are switched to the right 1 bit. If the two bits differ 1, 0 or 0, 1, then the multiplicand is added to or subtracted from the A register. Follow the addition or subtraction, the arithmetic switch right occurs. The both algorithm is going to end when the last count is equal to 0. If the count is not equal to 0, we will repeat the cycle until the end is equal to 0. Now, we are going to example -4 times 7 equal to -28. First, multiplier -4 and multiplicand are played in the Q and M register respectively. This is also a 1-bit register played logically to the right of the least significant bit Q0 of the Q register and designated Q-1. The result of the multiplication will appear in the A and Q register. A and Q register are initialized to 0. Control logic scan the bit of the multiplier one at a time. Now, as each bit is exempt, the bit to its right is also exempt. The two bits are the same, 0, 0, then all of the bits of the A, Q, and Q-1 register are shifted to the right 1 bit. So now we see the two bits are different. Now the count is not equal to 0, it's 3. Then we repeat the cycle. The two bits are the same, 0, 0. Then we repeat all of the bits of the A, Q, and Q-1 register are shifted to the right 1 bit. Now the count is 2, so we repeat the cycle and we are going to the third cycle. Now the two bit is 1, 0. Then the multiplicand is subtracted from the A register. From the subtraction, the arithmetic shift right occurs. Now the count is 1, so we repeat the cycle. Since the two bits is 1, 1, then all of the bits of A, Q, and Q-1 register are shifted to the right 1 bit. The both algorithm is end since the last count is equal to 0. When we get since the first digit is 1, we know the answer is negative value. Then we are going to do complement plus 1. Then we will get the value 11100, which is equal to 28. And now we are going to talk about division. Division is somewhat more complex than multiplication, but it's based on the same general principle. First, the bits of the dividend are exempt from left to right. until the set of big exams represent a number greater than or equal to the divisor. Until the event occurs, 0 s are played in the quotient from left to right. When the event occurs, A1 is played in the quotient and the divisor is subtracted from the partial dividend. The result is referred to as a partial remainder. The division follows a cyclic pattern. At each cycle, additional bits from the dividend are expanded to the partial remainder until the result is greater than or equal to the divisor. The process continues until all of the bits of the dividend are exhausted. This is flowchart of unsigned binary division. First, the divisor is placed in the M register, the dividend in the Q register. At each step, the A and Q register together are shifted to the left 1 bit. M is subtracted from A to determine whether A divides the partial remainder. If it does, the Q0 gets a 1 bit. Otherwise, Q0 gets a 0 bit and M must be added back to A to restore the previous value. The count is then decremented and the process continues for n steps. At the end, the quotient is in the Q register and the remainder is in the A register. Register together are shifted to the left 1 bit. Then, M is subtracted from A to determine whether A divides the partial remainder. When it does, the Q0 gets a 1 bit. So, when the first digit is 1, the Q0 is 0. Then, M is added back to A and to restore the previous value. After that, the count is then decremented. Since the count is not equal to 0, we will repeat the step. The A and Q register together are shifted to the left 1 bit. M is subtracted from A to determine whether A divides the partial remainder. When the first digit is 1, then Q0 is 0. Then M is added back to A to restore the previous value. After that, the count is then decremented. Now, A and Q register together are shifted to the left 1 bit. M is subtracted from A to determine whether A divides the partial remainder. When it does, the Q0 gets a 1 bit. Now, the first digit is 0, then Q0 is 1. So, M no need to add back to A. The count is then decremented. A and Q register together are shifted to the left 1 bit. M is subtracted from A to determine whether A divides the partial remainder. When it does, the Q0 gets a 1 bit. Now, the first digit is 0, then Q0 is 1. So, M no need to add back to A. Since the count is 0, we get the remainder and quotient which 0, 0, 0, 0, 1 and 0, 0, 1, 1.